The Earth intercepts a lot of solar power, 173,000 terawatts. That's 10,000 times more power than the planet's population uses. So is it possible that one day the world could be completely reliant on solar energy? To answer that question, we first need to examine how solar panels convert solar energy to electrical energy. Solar panels are made up of smaller units called solar cells. The most common solar cells are made from silicon, a semiconductor that is the second most abundant element on Earth. In a solar cell, crystalline silicon is sandwiched between conductive layers. Each silicon atom is connected to its neighbors by 4 strong bonds, which keep the electrons in place so no current can flow. Here's the key. A silicon solar cell uses 2 different layers of silicon. An N-type silicon has extra electrons, and P-type silicon has extra spaces for electrons, called holes. Where the 2 types of silicon meet, electrons can wander across the PN junction, leaving a positive charge on one side and creating negative charge on the other. You can think of light as the flow of tiny particles called photons shooting out from the sun. When one of these photons strikes the silicon cell with enough energy, it can knock an electron from its bond, leaving a hole. The negatively charged electron and location of the positively charged hole are now free to move around. But because of the electric field at the PN junction, they'll only go one way. The electron is drawn to the N side, while the hole is drawn to the P side. The mobile electrons are collected by thin metal fingers at the top of the cell. From there, they flow through an external circuit, doing electrical work like powering a light bulb, before returning through the conductive aluminum sheet on the back. Each silicon cell only puts out half a volt, but you can string them together in modules to get more power. 12 photovoltaic cells are enough to charge a cell phone, while it takes many modules to power an entire house. Electrons are the only moving parts in a solar cell, and they all go back where they came from. There's nothing to get worn out or used up, so solar cells can last for decades. So what's stopping us from being completely reliant on solar power? There are political factors at play, not to mention businesses that lobby to maintain the status quo. But for now, let's focus on the physical and logistical challenges. And the most obvious of those is that solar energy is unevenly distributed across the planet. Some areas are sunnier than others. It's also inconsistent. Less solar energy is available on cloudy days or at night. So a total reliance would require efficient ways to get electricity from sunny spots to cloudy ones, and effective storage of energy. The efficiency of the cell itself is a challenge too. If sunlight is reflected instead of absorbed, or if dislodged electrons fall back into a hole before going through the circuit, that photon's energy is lost. The most efficient solar cell yet still only converts 46% of the available sunlight to electricity, and most commercial systems are currently 15 to 20% efficient. In spite of these limitations, it actually would be possible to power the entire world with today's solar technology. We'd need the funding to build the infrastructure and a good deal of space. Estimates range from tens to hundreds of thousands of square miles. Which seems like a lot, but the Sahara Desert alone is over 3 million square miles in area. Meanwhile, solar cells are getting better, cheaper, and are competing with electricity from the grid. And innovations like floating solar farms may change the landscape entirely. Thought experiments aside, there's the fact that over 1 billion people don't have access to a reliable electric grid, especially in developing countries, many of which are sunny. So in places like that, solar energy is already much cheaper and safer than available alternatives like kerosene. For, say, Finland or Seattle, though, effective solar energy may still be a
Hello! Solar cells produce electricity, reliable and without the need for any operating supplies, simply with the power of the sun. We are fascinated by this technology, together with many millions of people who already draw electricity from the sun with big and small solar plants. We from GP Solar and Solmic provide our supporting services, so solar modules can be produced at a low price in huge integrated factories, and solar energy can at last become a more important part of power production. I invite you to discover the making of solar modules together with me.
An integrated solar factory with a production site for the metallurgical silicon, the big polysilicon plant, the crystallization furnace for ingot production, the wafer production, the solar cell production site, and the module factory. There is also a central administration building, as well as optionally a solar cell academy and an own solar power plant.
In the beginning there is sand, silica sand to be exact, since it contains mainly silicon dioxide from which we extract the precious silicon. By the way, silicon is the second most common element in the Earth's crust, so we won't run out of it. Together with coal or other source of carbon, the silicon sand is melted down at over 2000 degrees Celsius. The result is metallurgical grade silicon, with a purity of almost 99%. When it cools down, metallurgical grade silicon solidifies into a shiny crystal, such as these.
Metallurgical grade silicon can be made of nearly any kind of sand. Still, it makes sense to use very pure materials. Herewith, a purity of already 99% may be reached. To produce it, the silica sand is put in a furnace together with a source of carbon. This alloy is melted down at 2000 degrees using an electric arc. In this process, the oxygen and silicon bonds are broken and carbon dioxide and the silicon that we want to extract are formed.
No great difference at first sight, metallurgical silicon and polysilicon. But this one still contains 1% of impurities, while solar power production needs a purity level of at least 99.999999%. Such a high purity can only be produced by liquefying the silicon, cleaning it by distillation, and finally depositing it onto a silicon seed sample.
The metallurgical silicon will be cleaned to a very high purity in the polysilicon factory. Since it is very difficult to clean it in its solid state, a chemical process is done. The chunks are milled and liquefied, and then this fluid is cleaned in a distillation process. This happens in the high towers that can be seen here. Afterwards, it is directed into the so-called Siemens reactors. And this is how the purified gas is transformed into highly pure silicon. The gas is fed into the reactor where it deposits on the bars. In order to process the silicon in the next step, it is broken into pieces again and then carried to the ingot factory.
Pure silicon, the basis for our solar power production, is created. But how can we make the electrons flow in the silicon? What makes our little water pump work just with the power of the sun?
A silicon solar cell. It can create electricity because of this trick. During the manufacturing of ingots, boron is added to the silicon. And later, during the processing of a cell, phosphorus is diffused into the silicon. As a result, two different layers are created. The region between the layers creates a kind of wall for the electrons. They cannot get past this barrier by themselves, but by the help of photons they can overcome it. Now, more and more electrons gather at the upper side of the solar cell, where they push each other aside, but they cannot cross back because of the barrier. By connecting the upper and lower side of the cell with a conducting wire, the electrons can return through this wire.
To this point, we have produced highly pure silicon. This is also used in the microelectronic industry. In order to produce solar cells, impurities must be added systematically. At first, boron is added. Afterwards, an ingot of silicon is manufactured, either as a block of solidified multicrystalline silicon or as a single crystal of monocrystalline silicon pulled from molten silicon. Both are possible ways, but in the following we will have a closer look onto multicrystalline silicon only.
For the first time, we are in a clean room. The chunks of polysilicon are filled in a crucible, and then a vial of boron is added. Altogether, it is brought into the crystallization oven, where it is melted. By regulating the cooling, it is possible to remove unwanted substances. Once the silicon has solidified, the crucible is removed and the ingot is carried to the nearby wafer factory.
Just gently pressing and the cooked egg is split into many slices. The next production step, the wafering, works in a similar way. The first cutting creates bricks with the correct edge lengths. These are then cut into very thin slices, each less than 0.2 millimeters thick. These wafers are then used for producing the solar cells.
The wafering is done in two steps. At first, the ingot. This large block coming from the ingot factory is cut into bricks. Then these are pushed through a wire saw. In it, a several hundred kilometers long wire, carrying the so-called slurry, is put through the brick. It contains finest parts of silicon carbide, which cut the wafers out of the brick. They are then cleaned in a bath and afterwards carried to the nearby cell production.
We have now passed through the first factories and our silica sand has turned into these wafers. In a factory like this, the crucial part of the barrier in the solar cell is formed and thereby the positive-negative junction in the cell is created. During this process, cleanliness is of utmost importance, since even low levels of impurities cause a bad efficiency of the cell. For this reason, the production facility is treated like a clean room and the operators must all wear special overalls. To get such a solar cell, in the end, the wafer must run through the following steps.
Here the wafers arrive. Several measuring devices guarantee a high quality of the end product. Then the surface of the wafer is roughed by running them through a chemical fluid. Now, in an oven at 900 degrees, the important step occurs, which converts the semiconductors into a solar cell. Phosphorus is diffused into one side of the cell. In order to be able to pick up the electrons later on, a grid of fine silver stripes is printed on the cell. Now, several cameras examine the cells to check the result and to measure the cell efficiency. Finally, the cells are sorted by certain criteria, and and then carried to the module factory.
By now, each cell can already produce electricity. In order to obtain greater power output and to offer a long lifespan, many cells are packed together in modules. Now they can provide power for 25 plus years simply once they are exposed to sunlight. By the way, in about 2 years, they have produced the energy that is needed for the entire production, including setting up. They can be mounted on facades, on rooftops, or even in great open-air plants. How these modules are produced can now be seen in the animation of our sixth and last factory.
In the beginning of the module factory, there are packages of solar cells, each containing cells with similar electrical characteristics. They are first placed in a row and then soldered together. Then these rows are placed next to each other and connected. In order to ensure that the module can produce electricity during its entire lifespan of more than 20 years, a sheet of glass is used for protection. An extra foil repels water. Then the modules are bonded in an oven. A flash simulating the sun under standard conditions tests the modules before they are packed and shipped to the customer.
About 3 watt can be produced by one solar cell, more than 200 by a module. An ordinary rooftop is big enough for approximately 5 kilowatt, so an average house will produce more electricity than the residents can use. Solar power is also getting cheaper, and plants with several megawatt have been built in open spaces, functioning as entire power plants. They herald the change to renewable energies and already represent a significant part of our energy supply. The modules are produced in highly specialized and increasingly integrated factories. GP Solar in Solmik would be delighted to help you in planning and implementing an integrated state-of-the-art factory.